In the last video, we derived the Biot-Savart law. It works for any current distribution, but it requires integrating the contribution of every single current element. That can get painful. Today we'll see a much easier tool, Ampere's circuit law. It plays the same role for magnetostatics that Gauss's law played for electrostatics. When the geometry is symmetric, it hands you the magnetic field in just a few lines. Picture a long straight wire carrying a steady current I. The magnetic field lines form perfect concentric circles around the wire. Now imagine walking around the wire along one of those circles. The path we take is called an Amperian loop. Ampere's law connects the field along this closed loop to the current passing through it. Here is the statement. The closed line integral of H dotted with dl around any closed path equals the total current enclosed by that path. Written as an equation, the loop integral of H dot dl equals I enclosed. On the left side, we walk once around the loop and sum up the component of H along our direction of travel. On the right side, we count how much net current pokes through the surface bounded by that loop. The direction convention follows the right-hand rule. Curl your fingers along the path, and your thumb points in the positive direction for enclosed current. So, how do we actually use this? 4 steps. First, identify the symmetry of the problem. Ampere's law is only easy when you can argue, by symmetry, that H has constant magnitude along some simple path. Second, choose an Amperian loop that matches that symmetry. For an infinite wire, a circle around the wire is perfect. For an infinite sheet or solenoid, a rectangle usually works. Third, evaluate the line integral. If H is constant along the path, the integral becomes H times the path length. Fourth, count the enclosed current and solve for H. That's it. Let's apply this to an infinite straight wire. By symmetry, H can only depend on the distance ρ from the wire, and it must point along a hat phi, circling the wire. Choose an Amperian loop, a circle of radius ρ centered on the wire. On this loop, H is constant in magnitude and always parallel to dl. So the line integral of H dot dl is just H times the circumference, which is H times 2 pi ρ. The current enclosed is simply I, the current in the wire. Setting the two sides equal, H times 2 pi ρ equals I. Solving for H equals I divided by 2 pi ρ in the a hat phi direction. Compare this with what we got from Biot-Savart last time. Exactly the same answer, but now in 3 lines instead of a full integration. Ampere's law also has a differential form. Apply Stokes' theorem to the left side. The loop integral of H dot dl becomes the surface integral of curl H dotted with ds. On the right side, the enclosed current is the surface integral of the current density J dotted with ds. Since this holds for every surface, the integrands must match. That gives us curl H equals J. This is one of the 4 Maxwell equations, the point form of Ampere's law for steady currents. It tells us that wherever current flows, the magnetic field has a curl. To wrap up, Ampere's circuit law says the closed line integral of H around any loop equals the enclosed current. In differential form, curl H equals J. When your problem has symmetry, cylindrical, planar, or solenoidal, Ampere's law is the fastest route to the magnetic field. In the next video, we'll apply it to 4 classic geometries: infinite wire, coaxial cable, infinite sheet of current, and the solenoid.